Good afternoon, all of you. Please let me know if I am audible. Oh, thank you. So we will be starting at sharp 4. So, good afternoon, everyone again. My name is Tushar, and I am an application engineer at Integrated Microsystem. Welcomes you all in this FDP program, Faculty Development Program. This is our seventh FDP. Previously, also we have done various webinars related to various research topics like batteries, magnetic properties, 2D materials, etc. So our today's topic is about empowering materials and device innovation using GPU acceleration and machine learning, how we can use GPU acceleration in the SynopsysQuantumATK software. So in this session, I will walk you through the presentation to explain how GPU acceleration computing and machine learning potentials are transforming materials and device simulation. Following that, Mr. Deepak will take over to you for the live demonstration of SynopsysQuantumATK, showing its latest capabilities in action. So this is going to be our presentation flow. We will go through basic terminologies. We will recap about this software, SynopsysQuantumATK, and why GPU and machine learning parts are essential in various simulation, and what domain the Synopsys team have introduced about this GPU accelerations. And that job manager part, like, and what part the DFT LC performance, and what are the time complexity or the reduction in time complexity we get after enabling the GPU acceleration in this software. So this is going to be the presentation flow. So QuantumATK is nothing but it is the DFT based software. It's the advanced atomistic simulation tool in which one can create and simulate atomic structures at nanoscale. So these are the four important pillars of this software. The first one is density functional theory, and the second one is semi-empirical tight binding. Then for the larger structures, we do have classical and machine learned force field, and for the device simulation, we do have a non-equilibrium Green's function. So when we pronoun about this software that it is DFT based, it is not just only DFT based. So here you can see we do have a complete set of simulation engines to deal with the various categories of the structures and the properties as well. So mainly if we talk about the DFT, we do have a two basis set, that is a plane wave basis set and the linear combination of atomic orbital basis set. Yeah, one more thing. If you have any doubt, you can interrupt me at any point. Yeah, after setting up the basis set in your calculator, now you can set the pseudo potentials, Bernoulli zone root, density mesh cutoff, and other properties, and the numerical occupation method that should be involved to proceed the simulation. After that, we do have a semi-empirical tight binding, for which either you can use the Slater-Coaster method and the extended Huckel method, and the density functional tight binding as well. And after that, we do have a module called classical and machine learned force field. So machine learned force field gives you the accuracy nearer to the ab initio methods. And the classical force field deals with when we are dealing with, actually it is a mathematical model that describes the potential of the system in accordance with the forces, stress and energies of the atoms within a structure. So for the non-equilibrium Green's function, actually at the for the device simulation, at the two stages, that is equilibrium and non-equilibrium state, we use this Green's function and the sparse Green function. So at the non-equilibrium state, when we are using the Green's function, that is what this module is called as non-equilibrium Green's function. So this platform software gives you the complete simulation set in this single platform. So it's a comprehensive platform. Any type of users, if you are at any level, you can directly start using this software by just referring the manual and the software. So there is no any necessity to learn anything etc. before using this software. Although it supports the Python as an input language. If you know Python, then you can directly give an input to this software by manipulating the Python script that it generates while creating the workflow. So it gives you these synergetic solutions, whether you're dealing with electronic, optical, mechanical, thermal, optoelectronic properties. Also, you can integrate this software with other tools. There are various set of export and the import capabilities this software has. Even if you have a raw data, like just an atoms and all the Cartesian coordinates, so you can design your structure by using the scripting part. So if you are going to set all the parameters accurately, you are going to get results very near to the experimental one. So GPU acceleration has emerged as a critical enabler in modern materials and research, allowing us to dramatically reduce simulation times for high complex systems. So traditional way actually, those based on DFT are very time consuming. So when we apply to a realistic structure like large structures, nano devices, and the amorphous materials with hundreds or thousands of atoms, GPU help overcome this by massively parallelizing the most demanding tasks such as SCF calculation or the diagonalization or the electronic structure analysis. So in quantum ATK, in the new update, we have seen that it is steepened up by 14x speed up for DFT calculation and even greater improvements up to 58 times in molecular dynamics when using a machine learned potentials. So this allows us to simulate not only a bigger systems but also a longer time scales, which is essential for studying diffusion defects, mechanical responses, and what used to take us several hours or even days now can be computed in a fraction of uh, time by enabling this GPU acceleration. So in this release of Quantum ATK 2025, introduce a robust GPU acceleration for both DFT and semi-empirical calculations, making the large-scale simulation far more efficient and accessible. So as I said, the traditional ways are not that much efficient if you are trying to calculate the band structure density of state by using the traditional SCF method. So it is very time consuming, and when you are using a CPU alone, especially for the system involving the hundred of atoms or the thousands of atoms. But with the GPU support now, quantum ATK offloads the most demanding part of the simulation, including matrix diagonalization and density matrix assembly onto the power parallel processor. So here you can see the example for a DFT simulation of bulk hafnium with 768 atoms showed a dramatic improvement. So a total calculation time dropped over 500 minutes on CPU to just 38 minutes when we are using a GPU, which representing almost 14 times speed up. Even more striking, the projected density of state calculation was just it's become much faster, about 37 times faster on a GPU. Similarly, for a realistic device simulation, a IK metal gate stack with the 916 atoms, you can see, when you're using a non-equilibrium Green's function calculation, saw a nearly 3 times reduction in the simulation time. So these improvements are not just numerical, they change what's possible, simulating large systems or devices that once seemed out cannot be reached by this traditional way. This means faster results, broader material exploration, ultimate more impactful research and development workflows. Importantly, all of these integrated into this existing quantum ATK GUI and the scripting workflows, so enabling GPU acceleration is seamless. Just select the GPU enable node in the job tool and the software handles the rest. Here you can see in this example, in the DFT-LC performance, especially for the bulk device level simulation, we have seen up to 2 times speed up in the self-consisting calculation, SCF calculation, and the geometry optimization when using a meta GGA or the GGA or Hubbard U functionals, that is a band gap correction method. This is particularly valuable for small to medium systems. Typically, above 100 atoms, where turnaround time used to be a limiting factor. Now, post SCF analysis, steps like projected density of state, pad band structure, and magnetic anisotropic calculations are now up to 5 times faster. So, for instance, in a test case, here you can see with the 162 atoms for crystalline SiO2 geometry optimization, the time dropped from 39 minutes to 20 minutes, and the PDOS analysis time dropped out from 10 minutes to just 2 minutes. This improvement, or even a more noticeable for systems with a multiple on-site orbital projections, where computation were previously more demanding. So another major upgrade is the ability to refuse the valence electron density from lower bases to speed up. So together, these enhancements significantly improve the DFT LCO workflows, whether you are optimizing your structure or you are trying to calculate the electronic properties or preparing a simulation for machine learned force field. So it's a strong step forward for research needing with a high accuracy without sacrificing the performance. So it also offers a complete and unified platform for working with the machine learned interatomic potentials, making it easier than ever to simulate a large scale accurate atomistic systems. So this includes supports for both user trained and the predefined models like MACE, M3GNet, CHGNet, and 7net, all of which can be used directly from the graphical user interface or through scripting as well. Whether you need a high accuracy or the rapid prototyping, QuantumATK allows you to balance speed and precise using these potentials. So with the new machine learned force field block in the workflow builder, now user can now easily select or import or train a model or apply D3 correction and can tune the hyper parameters. You can train custom models from scratch using your data or fine tune existing models or specific materials or process. So for example, a fine-tuned pre-trained MSE model for BEOL material, which reduces forces errors per Armstrong, showing how system-specific training specifically improves the accuracy. So the platform also allows seamless import and external machine learned force field that ASE compatible, including those bands on frameworks like DeepMD or ORB or MACE models. Specifically, you can even convert them into a QuantumATK native platform to use them in a standard workflows like geometry optimization or the diffusion. So this is a complete platform, gives you a full flexibility from deploying fast pre-trained models from explanatory studies to build a precise tailored potentials for production simulation. So it's an essential step forward in integrating with artificial intelligence with material simulation. So here you can see the diagram highlights the complete machine learned potential framework introducing in QuantumATK latest version. At the core, it begins with the trained data generated from DFT calculations. From there, user have three flexible paths to create or to use the machine learning potentials in simulation. So the first one is the training MTP model, which offers a strong balance between speed and accuracy, make it deal for the large scale system and the rapid simulation. The second one involves the fine tuning neural network based models like MACE model, which deliver higher accuracy and are better suited for the complex systems mainly, though they are typically slower than MTPs. The third and newly introduced path allows for importing external pre-trained and universal models such as 7net. This supports the rapid adoption of emerging MLP frameworks from the broader materials AI community. All three approaches are fed directly into the production simulation within this software QuantumATK, giving user full control over the trade-off between computational cost and the predictive performance. Yeah, one of the standout enhancement also that you get the machine learned force field block within a GUI now. So this block makes it incredible easy to work with the machine learned interatomic potentials, whether you are using pre-trained models or the custom trained ones. Within just a few clicks, now you can select the machine learning potentials like I described, MECE, M3GNet, CHGNet, or the 7net, or even custom moment potential you can train and can use in this software. The block offers a user-friendly interface to load the model, enable to disable D3 dispersion correction and modify model hyperparameter without needing to touch any code. So for researchers working with a large dataset or targeting specific material behavior, this block bridges the gap between AI and the production of the simulation. So these are the applications where machine learned force field can be applicable. So it is just opening an entirely new possibility for simulating complex materials at realistic time and length scale. So here you can see at first that the generation of amorphous material, that machine learned force field dramatically reduce the simulation. For example, on 80 picosecond molecular dynamic simulation, when we are using a machine learned force field, SiO2 structure, it generates around 600 atoms within an 11 minutes. At the same time, when we are using a DFT calculator on 16 cores, it took 10 days by using a traditional way of DFT molecular dynamics. So this kind of speed up is critical for materials like PC RAM, RE RAM, or you are working on a novel memories, even solar cells. Next, we have the simulation of complex interfaces and multi-layer stacks, essential in semiconductor and research and development. So QuantumATK allows us to build and optimize these structures using the multi-layer builder GUI. A great example is the creation of nearly defect-free crystalline or the amorphous high-K metal gate stack with the layer of silicon amorphous or SiO2 or hafnium or the TiO2 structure. So these type of simulations are crucial for modern CMOS or the MRAM technologies. Also, machine learns allow for realistic modeling of glassy amorphous materials with the impurities or important in the electronic optoelectronics actually. So one example induced 1,20,000 atom sodium silicate glass system simulating with the sodium impurity at 2,500 Kelvin. Something that would be practically impossible, but you can try to create a similar workflow in this software by using the machine learned force field, which can be initiated by the ab initio method. So another powerful use case in the study of crystallization and amorphization process in the memory materials like GESB or TE. With the machine learned force field, we can now simulate nanosecond long phase transition in systems with the thousands of atoms, capturing the dynamic necessary for device reliability and the performance analysis. We also use this machine learned force field to evaluate the thermal properties, including conductance, heat dissipation of systems, within the different interfaces, or even for the monolayer of the like MOS2 have been studies using the reverse non-equilibrium Green's function and the molecular dynamics. So yeah, for this thermal transport part, you have to use the non-equilibrium Green's function along with the NS long reverse molecular dynamics condition. So the results are closely matched with the experimental and the DFT benchmark. Finally, the machine learned force field are being used in surface process modeling such as thermal ALD and the ALE. In real case in simulation of HCCl4 deposition on HFO2, where the adsorption energy, the stacking coefficients and the converge values aligned well with the DFT predictions. So these simulations provide a critical inputs for feature scale processing modeling. Overall, machine learned force field are not just a speed enhancement, they enable entirely new class of simulation, making them indispensable for modern materials and the device research. One of the most powerful addition again is the ability to use the both newly added pre-trained and the universal neural network potentials and the custom trained MTP potentials, giving users an unpredictable range of flexibility in accuracy, speed, and the ease of deployment. So first, let's talk about the pre-trained universal models. This includes a neural network potentials like M3GNet, CHGNet, or the 7net, which are trained on the massive database and designed to work across a broad range of materials without requiring a system-specific tuning. So their advantage is immediately usability. Now you can load them directly onto the QuantumATK GUI or the scripting interface and can begin simulation within a minute. So this is the special useful for rapid screening or prototyping or exploratory research where you want result fast with the reasonable accuracy. On the other hand, we have options to train a custom MTP potentials, moment tensor potentials, which offer a very attractive balance between speed and accuracy for large scale systems. These are particularly useful when you have DFT reference data for a specific system or processes. So MTPs are the fast, efficient, and can handle the systems with the hundreds of thousands of atoms which are ideal for geometry optimization, molecular dynamics, and stress strain analysis. So together, these two classes of potential serves better, different but complementary purpose. Universal force field are the perfect for general purpose or the early stage research, while the custom moment tensor potentials shine in targeted production level simulation, where system specific behavior matters. And best of all, quantum ATK interface make both the paths accessible even to user with the limited machine learning experience, though it workflow builder and model import tools will help you. If there is any issue with your workflow, that there will be a cross sign which will indicate you whatever the issue with your workflow. So QATK takes a major leap forward by allowing a seamless integration of external open source machine learning potentials as well. So removing a key barrier between a cutting edge model development and a practical production level simulation. With this update, you can now directly import and use machine learning potentials trained outside of quantum-ATK using a popular open source workflow framework like MACE, CGH, or the DeepMD, and others without the need of the complex convergence or the custom coding. So these models can be loaded on this atomistic simulation environment compatible characters, or in the case of MACE converted to quantum-ATK native format using a dedicated utility. So this native integration significantly improves performance and stability, making it ready for the large scale simulations like in transport properties or the molecular dynamics. So the seamless workflow empowers research to rapidly test, benchmark, and deploy the newest AI-driven models for the community, bringing you closer to the latest innovation in material science. It also encourages cross-platform collaboration. You can now train a model using your preferred machine learning environment and immediately bring into the quantum-ATK for visualization and analysis and high-performance simulation. So yeah, here you can see this flowchart gives you the illustration like how we can import that data on this atomistic simulation environment, which is a machine-based learned potential, such as 7net or the CH3net with quantum-ATK simulation. In the workflow begins by installing the external MLP within a Python script, the external with the Python virtual environment. So once the model is set up, it can be imported into a quantum-ATK using the external machine learning force field calculator block. So this allows the model to directly embed it into the quantum-ATK simulation workflow. From here, now the machine learning potential can be used to compute energies, forces, and stress and run full-scale simulation like molecular dynamics, structural properties, studies, etc. So this seamless integration between this external MLPs can help you whether you are testing MLP in other software, so you can directly import and analyze in the software as well. Also, this diagram gives you the illustration like customizable MAC fitting framework now available in this quantum-ATK. So the process starts by combining the system-specific training data, the original universal MACE dataset or the pre-dataset that is already you have simulated, or the MACE multi-layer perceptron data. So these inputs are used in custom fitting routine, which fine-tunes the neural network potential for target material on process. So the comparison highlights the impact of the fine-tuning of retained MACE models for specific material system using quantum-ATK. On the left, you can see HK high K metal gate stack, where the force prediction error is dropped significantly from 0.45 electron volt per Armstrong when using a universal MACE M3 model to just 0.21 electron volt per Armstrong after fine tuning. Similarly, for the BEOL application involving CUMN alloy or interface So the fine tuning when we are using a MACE model just reduced from 0.73 electron volt per Armstrong to 0.27. So this demonstrates how customizing the model with the additional system specific data significantly improve accuracy for complex real world semiconductor applications. So simulating atomic structures diffusion at room temperature presents a major computational challenge such as event or extreme rare and occur over a long time scale that standard molecular dynamics cannot be efficient. So traditional molecular dynamic methods require excessively long simulation time to observe meaningful diffusion behavior. So especially at low thermal temperature, low energy, to overcome this, QuantumATK introduced the CVHD method, that is collective variable hyperdynamics method, an advanced accelerated dynamics technique. So CVHD works by applying a carefully designed and adaptive bias potentials along a selected collective variables such as bond length or the atomic position or the bond angle. This effectively lowers energy barriers from infrequent transitions, enabling the system to sample rare diffusions event more frequently. So what makes this CVHD particularly powerful is its ability to recover unbiased simulation time, known as the hyper time. That is why it is called as a collective variable hyperdynamics method. So this ensures that the results remain physically accurate despite the artificial acceleration. For example, CVHD can simulate the equivalent of hundreds of nanoseconds of diffusion within just a nanoseconds of compute time, offered to speed up 100x at the simulation. So this makes it possible to study critical diffusion phenomena at room temperature, such as hydrogen migration in material dopants and diffusion in semiconductors, or interface transport in complex materials, all within a practical simulations time. So QuantumATK also allow user to easily use this CVHD in graphical user interface builder, make it accessible for both. So here you can see for the acceleration of ion dynamic simulation, the MLPs such as MAC or M3GNet or MTPs model. These advanced models bridge the gap between the quantum mechanical accuracy and the classical simulation speed, making it feasible for to study large scale elastic systems under the practical computable time as well. So for the example here you can see when we are using just one CPU node with a 40 threads, the turnaround time, minimum turnaround time actually for the 200 molecular dynamics step is about 91 seconds. And at the same time, when we are using 4 GPU along with that, so it becomes 21, which is almost speeding up the simulation process by 4 times. So also here you can see QATK now supports the multi GPU acceleration for this machine learned models and the matter stem neural network potentials, which significantly enhances the speed and the accessibility of the molecular dynamics simulation. So these machine learned potentials, already known for their accuracy, which is near to the DFT method, now can be leveraged with the power of multiple GPUs to simulate much larger structures and longer time scale. Previously, beyond reach for the most users within the introduction of multi-layer GPU support, now simulation benefit from linear scale with the number of GPUs, meaning the more GPUs used, the faster the simulation you have. So here you can see the example. It is the structure which contains almost around 26,700 atoms, amorphous structure of TiS2. When running molecular dynamics with the MACE MTP set on 4A GPUs led to 58 times speed up when compared with a single CPU node. So reduce the total simulation time from an hour to just a minute. In comparison, a single GPU already offered a 16 times acceleration, but distributing the workload across the multiple GPUs drastically improved both the speed and the memory management. So this also enables handling larger systems over even more than 1 lakh atoms, since Each GPU now processes a smaller slice of the total memory demand. Again, we do have another improvement, that is about SPS, surface process simulation, uh, with the significantly enhanced in the accuracy, flexibility, and the stability of the simulation, involving deposition, etching, and the surface reactions. One key enhancement is to support for variable time step molecular dynamics, now which allow the simulation engine to automatically reduce the time step when atomic forces exceeded and at a certain threshold. So this prevents the unphysical behavior of during a high energy event such as ion impacts, or the enabling stable and reliable simulation without unnecessarily slowing down the entire simulation. Again, this is something that we will see in the live demonstration as well, like how we can use the GPU along with the CPU, how we can set nodes, whether we are dealing with any simulation. So these are some other enhancements. And GUI, the improve usability, speed of workflow creation, and expand modeling capabilities for both new and experienced users. One of the most significant addition is that there is a separate class of 2D material database directly into the Nano Lab Builder. So the database contains a wide variety of optimization of 2D material structures along with the compatible potentials, allowing user to rapidly set up the simulation involving 2D systems like Graphene, MOS2, and others. So user can now directly apply a matching force field via the workflow builder, ensuring both accuracy and convenience. So additional advancement to include a new crystal structure prediction block, which allows user to generate and analyze novel crystal structure within the GUI, so which is ideal for material discovery projects. So the movie tool can also be upgraded now. Now user can now change the color of a specific subset of atoms in the 3D visualization tool. So these enhancements reflect Synopsys committee to make QuantumATK not a powerful atomistic simulation engine, but also an intuitive visual platform for material modeling and the analysis. These are some other advanced enhancements. So it introduced several additions in the ion dynamic simulations aimed to improve the robustness, flexibility, and the convergence across the range of use cases. A key addition that support a new optimization algorithm, specifically velocity projection optimization and conjugate gradient optimizers, now are available for various simulation blocks. So these new methods improve stability and the performance in challenging simulations, particularly when default optimizers struggle to converge. They are now integrated into a tool such as elastic constant, optimized geometry, active learning optimization, adaptive kinetic Monte Carlo method, and even an optimized nudge elastic band, among others, providing a greater control and success rate in the complex atomistic system. So another practical feature added in this support for rigid body constant in the force-based Monte Carlo simulation. This enables user to constrain selected parts of a system, such as interfaces or embedded nanoparticles, while allowing the rest of the structure to evolve freely under the simulation. These are some other improvements in the MTP model as well. So making the process more efficient and consistent and easier to manage for user working with the machine learning interatomic potential. One key advancement is the ability to initialize new training or active learning simulation from an already trained MTP model by importing its nonlinear coefficients directly via the GUI of this load MTP file. So once you have the GUI, now you do not have to repeat that simulation again. Now you can also directly use a module called load from the file to directly import the file which have been already simulated. So performance improvements have been also made to the MTP analyzer, which now provides a faster and more insightful evaluation, model accuracy, and the stability. These upgrades help reduce training time and improve reliability and make it easier to deploy accurate MTP models for a wide range of materials, Whether used for standalone molecular dynamics or as a part of an active learning loop, these improvements greatly simplify the MTP development workflow, making it more accessible to both. Yeah, again, we do have a new saddle tool. So the adaptive kinetic Monte Carlo framework has been significantly enhanced within the introduction of two advanced saddle, that is the Lanzos saddle or search, and the ARTN, that is activation relaxation technique method. So these replace the previous high temperature MD based approach, offering a more efficient and the physically appropriate way to identify transition state in system where thermal acceleration is either an efficient or inelastic. So now the Lanzos method is now the default saddle search technique in adaptive kinetic Monte Carlo, providing both speed and accuracy, while ART is the especially effective for systems involving impurity or atoms or when you are dealing with the defects. Again, there are some improvements in the nudge elastic band as well. So a major enhancement is this introduction of the sequential IDDP method for initializing complex reaction paths. So this method improves how initial nudge elastic band images are generated, avoiding issues like broken bonds in cycloaddition or multi-step reaction. Now user can apply a spring skew method setting which increases the image density nearer to the transition or the specified range, which lead to the better resolution and faster convergence during the optimization. So for optimization itself, a new velocity projection optimization algorithm has been added, which outperforms the traditional LBFGS method in the pre-optimization step. In addition, a user can now have an option to automatically run climbing image, that is NAB image, after the standard NAB simulation. Yeah, so all these GPU acceleration can now be used in these advanced analysis. So this software supports these advanced analysis like molecular dynamics, optimized geometry, dynamical metrics. Whether you're dealing with the electronic property or the physical property, you can try to calculate the stress strain analysis. Or if you wanted to calculate the transition in between analysis, so that you can use this nudge elastic band along with this HTST event. Also, while using the optimization geometry block, you can try to find the most optimum structures to calculate the key properties such as bond angle, bond length, or the dihedral between the atoms. Similarly, you can use this dynamical matrix for various analysis like vibrational analysis. If you wanted to check for the different vibrations of any structure, or in Raman spectroscopy as well. Similarly, these are other following advanced analysis that you can perform in this software. Yeah, we do have a separate various types of kinetic Monte Carlo method as well, like adaptive kinetic Monte Carlo or the constrained one or the time stamped one, etc. Apart from that, you do have a privilege that you can also create a grain boundary for any bulk configuration as well, whether you wanted to convert it to the bulk grain boundary or the device grain boundary. So yeah, these are the advanced analysis. These are some compatible characteristics. If you wanted to calculate band structure, effective mass, or the exchange correlation potential, Gilbert damping, Heisenberg exchange, etc. Apart from that, yeah, you can also calculate the characteristics for the devices as well, like IV curve, device density of state, mobility, transmission spectrum, etc. So this release brings a wide range of powerful upgrade from GPU-accelerated simulations and fine-tuned machine learned potentials to enhance ion dynamics, surface process modeling, and the significantly improved user interface. So these advancements not only boost the computational performance and scalability, but also make the high accuracy, large scale atomistic modeling more accessible and intuitive. Features like multi-GUI support, MACE, new class of MLT, MetaSim, which is also a new class of MTP model, advanced nudge elastic band tools, and the real-time job management reflects Synopsys commitment to innovation in material science and the semiconductor research. So importantly, this release is not just a final destination. But a part of continuous journey, the Synopsys team remains actively engaged in improving quantum ATK, addressing such bugs and expanding feature and integrating the latest scientific advancement into the future versions. So that is from my side. Now, if there is any question related to the presentation, you can let me know. Otherwise, we can start with the live demonstration.
Hello?
Yeah.
Hello?
Yes.
Sir, am I audible?
Yeah, you are audible.
Sir, I am Dr. Janani from SRMIST. Actually, we are a sole user of QuantumATK. My complete work was done with QuantumATK on biosystems. Actually, the present scenario, only one thing is we are struggling with finding the solubility studies. Actually, we are designing drug delivery systems. Okay, so we are only randomly placing water molecule and studying microsolvation method. Is there any possibility to study complete solvation method? We have an option tool called solvation, but that is not working out. That's what I would like to ask you out.
Yeah, I think what we can do here, there is a separate plugin that is of adsorption. So you can try to place a water molecule or different sites and can try to optimize this structure by using this optimization geometry block. That I think we can cover in the live demonstration. I will show you.
Actually, we are doing like that only as microsolvation. But actually, what I need is you are telling about ionic liquids and all, na? Study and all. Na? So, like that, in Gaussian software, you have an option for solubility. Their entire system of water molecule will be placed covering the complete drug delivery unit. So, like that, is there any possibility? Because we have an option for solubility in the QuantumATK software which we have.
Yeah, so
If you could
that
help
thing
with
is,
us.
yeah.
So, that is the only part we are struggling. The thing is, we are keeping random water molecule and optimization rather than keeping a live explicit solvation method.
Okay. After this session, I will try to solve your query. If possible, you can
Okay,
share.
sir.
These are my contact details. Yeah.
Sure. I'll just save it. Just a minute. Yeah, sir.
So yes, Deepak sir, now you can start with the live demonstration. I think there are no more questions.
So thank you, Tushar, for this wonderful presentation about this GPU acceleration in the material and device simulation. So let me share my screen for the live demonstration of this QuantumATK software. So I hope my screen is visual to all of you. So this is the graphical user interface of this SynopsysQuantumATK that is called virtual nanolab. So firstly, I will give a brief summary about this virtual nanolab that we have. So this virtual nanolab will help you to create any kind of structure. Here you can see we have the various plugin toolbars. So this is the project section, and here you can see I have created multiple projects. So if you want to work on your existing project, you need to double click, and if you want to create a new project, then you can select this add option, define the directory, and you can define the project name. Then you can easily add a new project in the project section. So this is the data filter, and here you can see I have simulated multiple data. So if you want to filter out your data, you can see this is the data filter that we have. You can go with the everything like the created structure and also the simulated data by the QuantumATK. If you want to see only data, you can go with the only data option. Now you can see these are the data that I have already simulated. If you want to show the molecule configuration, so you can see. So you can also add your own data filter by selecting this new add option. So this is the builder that will basically help you to create any kind of structure, and this area is called stats. So whatever the structure we will create, that will store here. Here we can visualize the 3D view, and this is the advanced panel toolbar. So this advanced panel toolbar will help you to create your desired structure. Here you can see it comes with the various builder tools. Like we can create a FM cantilever TP structure, amorphous pre-builder, alloy structure, icosahedron, interface builder, nanoparticle, nanowires, even nudge elastic band. And here you can see it comes with the bulk tool option as well. So we can know the crystal information, we can fit the cell, we can merge any two unit cell, we can repeat our structure, even stretching the cell that is also possible. And now you can also create a supercell from the bulk configuration. So here you can see we have the option to create a device from the bulk configuration. Like we can go from the device from the bulk, and we can also go from surface to bulk. So this is all about the panel toolbar, and here you can see this is the workflow settings. So this workflow setting help you to set up your calculator and the analysis part. Here you can see in this simulation we have the multiple calculator, or we have the LCO calculator, we have the device LCO calculator, we have the plane wave calculator, or we have the semi-empirical, we have the device semi-empirical calculator, and here we have the classical force field calculator. And you can see this is the new improvement in this GUI, and here we have the machine learned force field calculator under the QuantumATK. And you can also go with the ground state calculator that will combine with the many body perturbation theory. And once you select your calculator part, you can go to the analysis. So you can see these are the list of analysis that you can go for the materials and devices simulation. Now you can see this is the job submission settings, and this job submission setting will help you to fire the job from GUI to the local machine. You can easily fire the job from GUI to the remote machine option as well. So in the remote machine, you can see we have the various options, or you can go with the new direct remote machine, local machine, LSF machine, PVS Pro, SG, and also you can create this SRAM machine as well. Now this is the editor. So if you are exporting writing the Python script, then you can also write your own scripting in the editor part, and then you can go for the job submission settings. And you can see this is the viewer. So we can visualize the 1D view, 2D view, and 3D view. So here you can see this is the online database of the QuantumATK software, and here we support the crystallographic open source database, and we also support the material project. So apart from this online database, it also comes with the local database, and here you can see this is the form database that we have. And in the local database, you can see we have the various material options. We have the list of molecules, or we have the crystals, or we have the fluorescent materials, we have the zeolite materials, monomers for the polymer simulation, and we also have the ground state elemental crystal. And here you can see this is the new improvement in this QuantumATK. They have added separate 2D material database. So this is the database option, and here you can see we have the import option as well. So you can also create your own data materials by selecting the load configuration from the file, and then you can easily add in the material section. So if you want to start from the scratch, you need to select this add option, and in the add you can see we have the new configuration. So once you select a new configuration, our default hydrogen element will be selected. So this is the hydrogen element with the fractional coordinate point 000. Now if you want to convert this structure as a molecule, then we have the pentagon sign. So this is the molecular builder, and this molecular builder will help you to create any kind of molecules. You can see we have the periodic table, so you can select your desired element. And here we also have the fragmentation, like we have the hydrocarbons, complex ring, simple ring, like you can see methane, ethane, acetylene, butane, decane. So any molecule as per your choice you can take, and then you can go to the molecule option. So once you create your desired molecule, again you need to select this pentagon sign, and now you can see the material has been added in this test, and this is the 3D view. So this way we can create any kind of molecule from the scratch, and here you can see this is the from file option. So these are the supported file format that we can easily import in the QuantumATK. Like we can support the we can import the Python file, SDF file, .car file, CIF file, XSD postcard file, contour file. So this file format we can easily import, and then we can do their various analysis by the different calculator settings. Now this is all about the local database, and here you can see we have the plugin toolbars. So in the plugin toolbars, here you can see we have the crystallograph open source database for importing the crystal, or we have the PubChem database for importing the molecules, and here we have the nanotube builder. So this nanotube builder will help you to create any kind of nanotube. Basically, we have to define the chemical properties. Then we can go to the bond distance. Then we can go with the inner tube, center tube, and the outer tube. So this way you can design the multiple nanotube. So if I go with the default value, you can see this is the carbon nanotube, and with the crawl vector 6 and 0. So we can also manipulate the crawl vector, and you can also enable the center tube and the outer tube as well. So this way we can design the multiple nanotube. So this is the carbon nanotube. Suppose if you want to design a new nanotube option, so we have to replace the site element from site A and site B. Like you can see, if I take the silicon element at the site A, then it will create a silicon carbide nanotube. Now you can see. And if you want to create a MOS2 nanotube, so first we have to take the molybdenum at the site A and the sulfur at the site B. Now we have to define the bond distance between the molybdenum and the sulfur, so that it will become MOS2. Now you can see I would like to go with the 1.6 angstrom and then select this preview. You can see this is the MOS2 nanotube. So as per your need, you can select the tube option, go to the preview, and once you're done with this nanotube builder, you can select this build option. So this way we can design any kind of nanotube structure. Similarly, you can see we have the crystal builder. So for creating any kind of structure, crystal structure, we should know all the information like the space group, like the triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, even the cubic structure, like the face center cubic structure and body center cubic structure. So once you select the space group, then their previous lattice will automatically selected, and then we can define the ABC value, alpha, beta, gamma value, and then this add option will be enabled, so that we can define the n number of element and then the fractional coordinate point. So once you done, you can easily create any kind of crystal structure. So let me select a face center cubic structure. Like you can see, this is the face centered. Here I would like to define the experimental value for the silicon material of 4.51. And now you can see this is the add option to add in the element into the crystal. Here you can see this is the default value and this is the hydrogen element. If you want to change this hydrogen, we have to double click, and these are the list of elements that you have in the periodic table. So you can go with any element as per your need. Like you can see this is the silicon material, and we can add n number of elements. There is no limitation. And here you can see we have the preview option. You can go with the primitive cell. You can also show the conventional cell. So this is for preview and this is for building the structure. So once you're done, you can select this build option. Now you can see the material has been added in this test, and this is our 3D view. So this way we can easily create any kind of crystal. And here you can see we have the nano ribbon builder. Similarly, we have to define the site element at the site A and site B. We need to define the bond length, and this is the passivation with the hydrogen element or inner structure. And then you can go with the geometry option. You can align with the crawl vector. You can also go with the zigzag and the armature structure. So let me align with the crawl vector. Now you can see. So this is the graphene nano ribbon, and here you can see this is the hydrogen passivation. You can also manipulate the crawl vector. Like you can see this is the 4x4. And if I take this zigzag, you can see this is the zigzag graphene nano ribbon. Similarly, you can go with the armature. So this way we can design or graphene any kind of a nano ribbon, and once you've done, you can again select this build option. Now here you can see we have the nano sheet option as well. Similarly, we have to define the chemical properties, bond length, and then we have to define the geometry option. And once you've done, you can select the preview and then select the build option. Now you can see this nanotube is quite thin. So if you want to increase the length in any direction, so we have to use the advanced panel toolbar. So in the advanced panel toolbar, we have the repeat option under the bulk tool. So you can also search your builder option from the panel toolbar. Now you can see this is the repeat, and we can repeat in A direction, B direction, and C direction. So for this nanotube, I would like to repeat in the C direction, and this is our transport direction. So I would like to take 10 times. Now you can see. So the length of this nanotube has been increased 10 times in the transport direction. Now this is all about the advanced panel toolbar that we have. Sorry, plugin toolbars. Now If I talk about the material simulation, including the acceleration of GPU, so this is our bulk configuration. Here you can see, we can show the information about the structure. So this is the bulk configuration, and in this structure we have total 480 atoms, and this is the lattice type. So this is the unit cell structure, and this is the primitive vector, and here you can see this is the unit cell volume, and this is the density of the unit cell. So this is the information about this bulk configuration that we have created. Now, if you want to include the GPU acceleration for the faster simulation, then you can go to the workflow settings. And in the workflow settings, we have to select the calculator first, and then we can go to the analysis part. So in the calculator, you can see we have the different kind of calculator for the material simulation. Either you can use the LCO calculator, plane wave. So if you are going to use this plane wave calculator, then it will take a lot of times, but it will give you the higher amount of accuracy as compared to the LCO calculator. Because in the plane wave calculator, it will also consider the vacuum as a matter. Here you can see there are some vacuum space in the unit cell. So during the plane wave calculator, it will also consider as a matter so that it can provide the higher amount of accuracy. But once you are selecting the LCO calculator, it will neglect the vacuum or space from the unit cell. Now you can see this is the LCO calculator that has been added. Now these are the basic parameters that we need to define before the simulation. If you want to include any kind of a spintronics application in your materials, then you can go with the spin, like the unpolarized, polarized, non-collinear with the spin orbit coupling. We also support the various sections correlation function, like local density approximation, generalized gradient approximation, meta-GGA, hybrid function, and this is the custom option. And based on the extents correlation function, here you can see we have the predefined potential set. So this is for the GGA, and you can also go for the meta-GGA, and this is for the hybrid functional. If you want to define your own predefined functional set for any extents correlation function, then you can choose the custom, and then you can take this workflow into the editor and you can write the script. So this way we can also choose the custom extents correlation function. Now here you can see we can also define the numerical accuracy, and in the occupation method you can see we have the various method. If you are dealing with the semiconductor and metals, then you can use this direct Fermi direct and Gaussian shimmering. And if you are going to deal with the conductors, then you can use the phasals and the cold shimmering method. And here we can define the temperature, density, cutoff energy, and we can change the K-point sampling method as well. Now you can see this is the iteration control, and here we can define the tolerance value and maximum number of iteration steps for simulating our materials. And here we can define the damping factor, number of history per step. You can also include the SCF iteration. So if you want to disable the SCF iteration, you can enable it. Now you can see if you want to define any kind of boundary of, condition in your materials, like we support the direct conjugate gradient and non-uniform with the grid conjugate gradient, multi-grid, fast Fourier transform, and fast Fourier transform for the 2 dimension that you can use in the devices simulation, so that you can change the like a periodic, Dirichlet, and also the von Neumann 1D condition. So these are the basic settings that we need to change before the simulation, and once you've done, you can go to the analysis part. And before analysis, if you want to optimize your material so that you can get the stable configuration, and based on the stable configuration, you can go for the analysis. So let me select the optimized geometry. So in the optimized geometry, you can see. So previously we have two methods, the LBF GS and the fire method. But in this new release, you can see we have the no optimization. You can go with the velocity projection optimization and also the conjugate gradient. So this will help you to optimize your structure, and we can change the maximum force tolerance. We can enable the optimized cell, maximum stress tolerance, number of step size, maximum step size. So once you're done with this optimization, you can add your analysis part. Now if I take the band structure, now you can see the band structure has been added. Similarly, we can add the density of state, device density of state. So you can do all the analysis like electronics properties, mechanical, thermal, optical, even Raman property you can easily simulate. So once your workflow is ready, you can go to the, you can also define the project name. So once you're done, you can go to the editor to generate the Python script. Now you can see this is the Python script, and this Python script is editable. So before simulation, if you want to change any parameter or if you want to add any more analysis part, then you can write the script. And once you've done, you can go to the job simulation settings. Now we have to set this Python file. And here you can see, this is the job simulation. And here you can see I have added this local machine. And also we have added the remote machine. So this is my local machine. In the local machine, you can see we have the job setups. We can go with the serial. So it will run on a single core. If you want to define the number of thread in a single core, then you can use this threaded. And if you want to define the number of processor and number of thread as well, then you can go with the multi-process parallel or for the faster simulation. So here you can see how we have the option to enable the GPU acceleration, and the GPU acceleration is not supported on the Windows OS right now, but the R&D team are working on that. So, so to take the advantage of GPU, enable the GPU acceleration. So I will show you how we can set up a new remote machine. So let me submit it on my local machine. Now this is the project that we have added in the project section, and here you can see we have the run option. So if you want to run the job, we need to select this run option, and here it will generate the log file. So whatever the background simulation is ongoing for this creator project, you will get all the information in the log file. So I am going to stop because I have already simulated. Now if I show you how we can set up a remote machine. So let me take a LSF machine. Here you can see in this way we can set up a remote machine by selecting the desired remote. Now you can see this is the computer settings. Here we can define the title, and then we can go with the connection. So either you can go with the remote SSH connection. You can also go with the password based. So we have to define the host name, and we need to define the port and the username, and then you can check the connection. So once you're done, you can go to the environment, and here we have to select the working directory and the ATK executable path, and then MPI exe executable path. So once you're done, you can go to the queuing system, and here you can see we can define the number of node for the GPU, and we can define the number of core for the CPU. So once you're done, you can go to the job setting, and here you can see we have the option to select the nodes at the GPU, and we can select the number of core at the CPU, and we can select the MPI processor per node at the GPU, and the number of thread as well. So let me select 10 number of node at the GPU, and if I take a 10 or number of core at the CPU as well, and now you can see. So we have the option to change the number of nodes that we are going to use at the GPU, and we can also change the number of core to use at the GPU, and we can also add the MPI processor per node or per GPU. And here we can enable the GPU acceleration for the fast acceleration. So once you're done with the machine settings, then we can go to the diagnostic, and we can check all the settings like connection setting, login environment, directory checking setting, file resourcing, ATK check, MPI check, and also the queuing system. All these settings, so once you're done, then you can easily set up a remote machine. And once your remote machine is set up, you can go to the workflow, and then we can take the workflow into the job submission settings, and then we can choose our remote machine. And we have the option to change the MPI processor as well. And here you can also go with the notification, and you can easily transfer the file from the client machine to the server machine as well. So this way we can easily create a remote machine, and we can easily fire the job from a GUI to the remote machine option as well. So let me show some of the features that have been upgraded in the latest version, like the machine learning technique, and also the room diffusion coefficient. So for the MTP, I have already created a workflow. So let me go to the workflow settings. Yeah, this is my project, and here you can see we have used a trained model by using the example of molecular dynamic simulation, and also I have created some more. Yeah, this. So this is the MTP training for the crystal and amorphous structure in the quantum ATK, and that is structured in the three stages. So this is the crystal training data, and it will help you to generate the crystal training configuration with the random displacement, and it will help you to calculate the training data like the energy, force, stress with the reference of the DFT calculator that we have added at the top of the workflow settings. So once you calculate the data, and then it will go to the crystal training data from the bulk of the training set, and it will give you a fundamental description of the material in question, and it will also be used to fit the MTP training in the second MTP stage. So here you can see we have the amorphous active learning, and it will fit an initial MTP to the crystal training data, and which is then used to run the iterative active learning geometry optimization and also the molecular dynamic simulation. So that we can identify the relevant configuration which are not represented in the initial training configuration, and then you can go to the final MTP fitting data, and we can generate an ensemble of MTP models and select the best fitted MTP, and that gives the lowest and comparable training and testing the error with this is respect to the reference of the DFT method. I can see we have created a reference configuration for the crystal, and we have also selected the amorphous structure. So let me show. Yeah, this is the combination of titanium and the silicon element that has been added in the crystal. So three configuration I have added in the crystal turning displacement with the different lattice type, and here I have added the amorphous structure as well. You can see this is the amorphous structure of the titanium and the silicon element. So once your simulation completed, then it will generate a find ways to fit interatomic potential, and that we can utilize further for the molecular dynamic simulation. So let me show the data. Here you can see I have already simulated, and here you can see this is the moment tensor potential active learning data. And if I select with the movie tool, the MTP analyzer, then it will give the plot for the energy, stress, and also the force. Here you can see we have the data type. You can go with the scatter plot. You can also go with the error histogram. So once you select, you can go to the load data, and here you can see we have the two options. We have the initial and we have the active learning MTP data. So once you select, you can go to the plot option. Then it will generate a plot for the energy with respect to atom and train force and also the stress. Now here you can see we can go with the data value. Now, if you want to utilize this interatomic potential in any other simulation, so let me show how we can do that. So first, we have to create a structure with the combination of titanium and silicon element. So let me add from the online database. So this is the crystallographic functional database, and here you can see I have selected the titanium and the silicon element from the periodic table, and then you can we can go to the search option, and here you can see it has find five different structure with the different crystal type. We have the face center, we have also the face center with the different cell volume, and this is the simple orthorhombic structure, and this is the hexagonal. So you can take any example and then go to the builder settings. Now you can see this is the structure that we have added. Now you can go to the supercell option so that you can create a complex structure. Now you can see this is the supercell. We can also go with the repetition. You can see if I take 4 times in the A direction and 4 times in the B direction and 10 times in the C direction, then apply. Now you can see we have created a complex structure. Now we can go to the simulation. You can see we have to select a calculator, and here you can see we have the machine learned force field calculator. We can select and double click, and here you can see we have the moment tensor potential, and here we will select our MTP data that has been trained by the active learning. So we can go to the browse option, and here this is the location of my project, and here you can see I can see the data has been added, and previously you can see it is showing the error, but once you're done you can see. So this way we can utilize our generated interatomic potential for the further simulation, and then you can go to the analysis part. Like if I take the molecular dynamic simulation, so within a minute it will simulate our desired materials, and in this structure you can see we have total uh, yeah, we have the 640 titanium and 640 silicon element. Now once you've done, you can go to the Java script, select the open. We can save the file, and here I would like to run on my local machine, and you can see I'm going with the single core. So at the single core it will take less than a 1 minute. Now till the simulation running, let me show how we can go with the room temperature diffusion technique. So for that I have already created a workflow in the data, and here you can see this is my workflow settings. Now you can see for the copper with the diffusion atoms hydrogen, we have created a structure. Here you can see in the middle one we have the hydrogen diffusion. So once you create, you can go to the machine learned force field calculator to add the pre-trained interatomic potential. So you can see we have the pre-trained QuantumATK MTP data. We also have the M3GNet. You can also go with the neural network. We can also tune our interatomic potential that we have in the local database. So if you want to tune, you need to include it, and you can go to the DFT functional set, and you can define the temperature dependent at the D3 cutoff energy. So once you've done, then we can also tune the local database of the interatomic potential. So once you've done, you can go with the molecular dynamic simulation without adding the collective variable hyperdynamics, and we can also go with the collective variable hydrodynamics in the hoop function method. So here you can see we have the all the method, and this is the collective variable hyperdynamics method that we have selected, and here we have defined their parameters. Like we can go with the temperature, we can go with the global exponent, we can go with the maximum distortion. So once you've done with all the settings, you can cancel it, and then you can go to the molecular dynamic simulation so that you can calculate the force, energy, and the stress as well. I have already simulated, so let me show the data. Here you can see this is without adding the collective variable hyperdynamics, and this is after adding this CVHD. So let me show. So here you can see after the addition of collective variable hyperdynamics, we have the option to select the acceleration, collective variable hyperdynamics, global distortion, hypertime, that we can check. Let me check this acceleration. Now you can see. This is the acceleration with the respect to time. We can also go with the hypertime or potential, and this is the reaction coordinate. And here you can see this is without adding the CVHD method. So this way we can easily calculate the diffusion at the room temperature for the any complex materials. And if I show you the simulation that we have run, yeah, you can see it has simulated within 1 minute or 4 seconds. Now for the 1280 atoms. Yeah, we have 1280 atoms. So let me show the file name, and then I will show you the data.
Sir,
Yeah,
hello.
yeah, hello.
Sir, CVHD model is what you are telling is the machine learning model, sir.
Yes, ma'am. By adding the diffusion at the room temperature.
No, no, already existing MD, we do not have this,
Yes,
no, we need
yes.
to add it.
Yes, you can go to the, like you can see, this is the, I have already created this workflow. For that, you can
Okay,
add this molecular dynamic simulation after the hook function.
okay, we need to add like
We can
molecular
easily
dynamics
rename.
CVHD.
Yes, yes, yes. Basically, we have renamed this molecular dynamics CPHD method. You can
Oh,
see
okay.
all the method are same. If I take
We,
this one.
we, we will be getting the complete PPT of this presentation, sir.
Yeah, sure. After this session, I will share to you.
Okay, sir. Sir, and
Okay.
basically these improvements are only for force field calculators, this machine learning approach.
There are a lot of like improvement in this latest version. They have added the like a 2D material potential set. They have also added the 2D materials, and they have added the like improvement in the nudge elastic band, and also with the like a collective variable methods, and also there are some improvement in the machine and potential as well.
Uh,
And in
they are
the one of the
they are
most,
yet to be implemented in LCAO and
yes,
plane
they
wave,
have
right?
also improvement, yes, for the faster simulation. And one of the most improvement is the GPU acceleration.
Okay, but because primarily we are doing only optimization with LCAO, that's what I asked. In LCAO, this molecular machine learning is not added, right? Am I audible?
Yes, ma'am. Can you repeat again?
In LCAO, machine learning is not implemented, right?
Yes, sir. So for that, first you have to create a inter-atomic potential by using the machine learning technique. And once your
Okay,
inter-atomic potential generated, then you can utilize for the like you can go to the classical force field, and then you can select, and then after that you can select your optimization setting. So let me show how we can do that. Suppose
okay,
I have created this structure, and if I want to like optimize by using the inter-atomic potential that I have already generated, so for that I have to select the workflow settings, and then we can go to the classical force field, and in the classical force field we have to select our generated potential set. So for that we have to select the, yeah, here you can see they have also added more option for the 2D material database. So you can go with the like choose a 2D potential set, and here you can see you can also generate your own data set. You can go with the auto generation. We can also go with the add option to add the new element. So all the options we have for adding the interatomic potential. And if I take that interatomic potential that I have generated by the MTP, then I have to go to the moment tensor potential, and here I have to select my location where I have done the simulation, and this is my MTP data. Now you can see the data has been selected. Now we can go to the optimization settings. So this optimization will take more than 1 to 2 minutes, I think, for the simulation, and this will provide the same accuracy as the LCO, because we have generated the entire thermal potential by the LCO calculator in the MTP.
okay, sir. Thanks.
Oh, okay, thank you.
So, I just want to know how to have the new potentials which are not defined in the quantum ATK to the software, like dot Vashishta file through the custom potential. Because I've tried to add it to the custom potential, but it is not supporting the dot Vashishta file. I want to know how to add an undefined potential into the quantum ATK, which is not predefined yet.
Okay, so you have already like entire potential set. So for that, once you have the potential set, so we can go to the let me add the classical force field. Yeah, this one, and here you can go to the file option. Let me show. This is the custom potential set, and here you can see we have the option to load our file, interatomic potential file. So may I know like in this format you have the interatomic potential? Yeah, hello.
Yes, sir.
So may I know like in which format you have the interatomic potential? Okay, now so after this
Can you
session you
please
can let
repeat,
me
sir?
know. We
I'm
will.
not understanding anything. Can you please repeat? I don't know what you asked me.
May I know like the format of interatomic potential that you have?
Vashishta, sir. Vashishta potential for SiO2.
A
And
system
form,
potential set. Yeah, I think that you can easily import by selecting the load from the file. That is supported in the quantum-ATK.
sir, but the dot Vashishta format is not supporting, sir. I can't click it. Like it is not supported for the view. I tried it multiple times. Dot Vashishta file is not
Okay,
supporting.
okay. Okay, now so after this session I will have a look on that and then I will let you know.
Okay, sir.
Okay, Ma'am.
Sir, and one more thing, I have a doubt on the non-equilibrium thermodynamic simulation, like NVT ensemble is there in the force field calculator. Na?
Yes, ma'am,
There,
let
I
me know.
want to know how to use the non-equilibrium, reverse non-equilibrium thermodynamic equations.
Yeah, so for that you have to create a device structure. So once you created a device, so let me show. We are going to convert this bulk configuration as a device. So now we have created a device configuration. We can go to the workflow builder, and here first we have to add the device calculator. So this is the device calculator that we have added, and here we have the option to change the equilibrium position, or you can go to the device algorithm. You can see this is the equilibrium and this is the non-equilibrium green function method and the sparse green function method. So both method we have in the quantum-ATK. Now can you let me know what kind of analysis you want after adding the like a green function method?
Yes, sir. I understood. The thing is, like, I'm asking in the molecular dynamics calculator. In the sense,
In the
there is
device,
a
right?
yes, sir. RNEMD, reverse non-equilibrium molecular dynamics, sir.
These are the method that we have for the device simulation in the molecular dynamics. We have the NV velocity variability, NVT, or NVT. You can also go with the Langevin method. So
Okay, sir.
here we don't have the option like to select the non-equilibrium. But you can do one thing, you can take this workflow into the editor and then you can write the script. But once we are going for a bulk configuration, you can see we have the option to select the non-equilibrium. Sorry, I have to select a workflow. This is the workflow. And here first we have to add the calculator and then the molecular dynamic. And here you can see we have the option, yeah, we have the non-equilibrium moment exchange under the bulk configuration.
Yes, sir. This is the one I asked before. The thing is, like, how I can apply the heat exchange, because like exchange interval is there, but I want to give the exact heat flux to the system to take the thermal conductivity of a system which I was like interested on, but I can't give
Okay, so
the.
you want to study the heat dissipation in your molecular
I want
dynamics
to
simulation.
provide the heat flux value, sir.
Yeah, that we also have at the like documentation site. So let me show how we can do that. This is the quantum-ATK. You can type the heat dissipation. Heat dissipation. You can also go with the molecular dynamic. The tutorial is also available for that application. Yes, ma'am. After this session, I will share a tutorial into you for the heat dissipation in the molecular dynamics. So this is my contact details. So after that, you can like share, you can share your query, and I will share all the like documentation and the tutorial as
Okay, sir. Thank you so much for your explanation.
well. Okay,
Thank you, sir.
okay, thank you. Yeah, so if anyone has any query, they can let us know. We will try to help you. And let me have a look on the chat box. Yeah, so for that kind of application, we had to create our desired stretch on 902 or with the 2 by 2 in the diameter. And then we can go with the like tube option in the spatial region so that we can create a graphic, get all around, fill it with transistor. And then you can manually like define your own parameter in the IV simulation. You can define the gate to source voltage or drain to source voltage from any point, either 0 to 1 or minus 1 to 1. Any point you can take, and then you can go for the simulation. Okay. Yeah, for the remote machine option, we have to install the QuantumATK at the remote machine as well. So once the installation complete, then you can go for the remote machine settings. Because here you can see we need to define the working directory at the client machine. If I take any machine, a RSF machine, here you can see we have to define the working directory, ATK executable path, MPI run, and we also have to define the export statement for the license of fetching. So the installation is required at that machine. So this is all from our side. So thank you so much to all of you for joining
Deepak
this
sir, I
session.
have a question.
Yes,
Hello.
sir.
Deepak sir, I have a question.
Yes, sir.
Sir, when you were making this MOS2 nanotube over there, I guess it was only MO, not like MOS, not S2, because there are only like two atoms, right? So this for carbon-carbon CNT, you had used carbon-carbon, and while making for NOS2, I had gone through the tutorial that this ATK manual they provide, and also using that same plugin, I find that I get two different structures for the same nano.
So
In the
basically,
plugin,
sir, for yeah,
yes, sir. In the plugin, while you were making this thing, MOS2 nanotube, at that time you had selected this
sir.
molybdenum
Once
and
you
this.
like define the bond length,
Yes, sir.
yeah. So once you define the bond length of between the molybdenum and sulfur for the MOS2, then you can create the MOS2 nanotube. But once you are taking a random like bond distance, then it will make a nanotube between the molybdenum and sulfur only, not the MOS2.
Okay, sir.
But
So,
once you define the perfect value for the bond length for the MOS2, then you can easily create a nanotube structure.
okay, sir. Thank you so much. And the other question I was having is, sir, right now, currently we are using four systems, and each system has this. What we are doing is, from one system we are porting to the other system and giving license to like two of the systems, individual license. So, can you make a separate this thing, workshop to for this remote control and all of this thing? Like how to make the remote control from one system to another system and regarding this thing.
Sir, I did not get your point. Can you repeat again?
What I'm saying is, what we in our lab, what we are doing is total we have 4 systems, and from
Okay.
one like we have like 4 licenses, and from one system we are putting to the other and giving like using 2 licenses individually into system from so like you were saying this remote desktop and all of these things, it was like bit complicated for me. So can we have this separate workshop for this, like
Yes, sure, sir. After this session, you can just drop a mail regarding this, regarding the same. Then I will revert back to this and with you. We will surely help you to, or like I set up the remote machine.
okay.
Sir, I have a doubt.
Yes, sir, please.
Yeah, I want to make a crystal structure where the structure has to be one has to be amorphous and other has to be crystalline. Like if I'm having Fe or Fe2O3 and I want to make it with silica SiO2, and the SiO2 I want to be in amorphous state, and iron has to be in crystalline state. How you can suggest me any idea how to make those hetero structure where one is amorphous, and for one which I know the crystal structure, for one which I can't get the crystal structure. Can you give me some suggestion?
Yes, sir. So for that, basically, we have the merge unit cell option in the quantum ATK under the advanced panel toolbar. So first, you have to create a amorphous material, and you need to also create a crystalline material. So once the material creation is done, you can go with the merge option, and you can merge these two unit cell in a single unit cell by the merge option.
Okay,
Like
I
if I
can
take
get.
this one,
I have gone through the steps, but I have what is my doubt is if a crystal structure, as I can define a crystal structure, like if I am doing it in an experimental, I can go with some XRD and I can say with the with the crystalline material I can go with the unit cell and other thing. For amorphous material, how to justify that this much is there with the amorphous state? For that, I need some suggestion. I will one for a single material I will have some idea about its crystal structure. For the other material, for the amorphous silica, how to get those thing data like that to compare experimental data.
also, sir, for that you can use the interfaces builder for the amorphous and the crystalline. So let me create amorphous material and a crystalline material. You can see this is the SiO2 amorphous material,
Okay.
and if I take any silicon material, this one, now we can go to the interface builder. Here you can see it will
Yeah.
make the interface between two material, and for more than two material you can go with the interfaces. So let me go with the interfaces because we have the two different type of units here. So I would like to add this silicon and then amorphous material. Now you can see, and then you can go to the recalculate option. Then it will create a structure. Now you can see there is no structure generating right now. Let me fix this one. Okay, what we can do, we can go to the this interface builder, and we can take this structure into the first one. Now you can see it has been added, and we can add the second one at the second side. Then it will generate the interface.
Okay, I can get this process. Actually, I have done that interfaces. The issue is that how many atoms I have to choose for amorphous material. I have to go with the stoichiometry
Sir,
or
it, it is a user choice. So there is no limitation in adding the number of atoms in any unit cell.
no, no, I'm not
So
asking
whatever the
about the.
atoms you
No, no,
want,
no. One and two. Actually, if I'm having a composite of equal ratio, then I have to go 1.5 on 1.5. I have to select the if the crystalline material has some 50 atoms means I have to choose 50 silica atom or
then
that, that's
yeah,
my
you can
question.
use the polycrystal, this one.
Okay, okay,
And here you can define the material ratio.
okay.
Like you can see, if I take the silicon material here
Uh,
and the amorphous material, here you can
okay,
define the material ratio for this first and second.
okay.
Yeah,
If I give 50,
like if I
50.
take the one, by 2, and then build the structure. I am going with the default value. Just I have changed the ratio. We have to change all the settings actually. If I take core and here face center, we have to define the size as well. So once you define all the settings, then you can go with the material ratio, and then you can easily create a perfect structure.
Okay, okay,
But that option is available in the quantum ATK,
okay, okay. Thank you. I
to
will try
define the
it.
material, the
I
ratio of
will
the
try
crystal.
it. Thank you.
Yes, sir.
Sir, but for these optimizations of the bigger system, can you hear me?
Yes, ma'am. Yes, ma'am. Tell me.
Optimization of these bigger systems, we can go only with the molecular dynamics, right? We cannot go with LCAO.
Ma'am, not the molecular dynamic. This is the machine and force field. Because the
Yeah,
optimization is not possible from the molecular dynamic simulation. It will be possible by the
yeah. Only
calculator
from
such
machine
as a
learning
real
force field.
flow plane wave.
Okay, from machine learning for force field, you can do optimization of thousands of items. Okay.
Yes, yes, right. So first you have to generate the interatomic potential for that material. If the
Okay.
interatomic potential is already available, then you can choose by the classical force field. If the interatomic potential is not available, then first we have to generate, and then we can go for the optimization.
Okay.
Yeah.
And that will
Okay.
take less time even if we are having more than 5,000 atoms,
Yes,
right,
yes,
sir?
yes, yes, yes,
Okay.
yes, right.
Thank you, sir.
Okay, ma'am, thank you. Okay, so once again, thank you so much to all of you for joining this session. So for any query, you can let us know by the email ID and also the given number. And after this session, we will surely share the a recording of this session to you. So once again, thank you so much to all of you. So I am going to conclude this session.